This particular vector m is the dipole magnetic moment or magnetic dipole moment. Wood cannot be magnetized because the existence of dipole moment actually determines if an object is magnetizable or not. Magnetic intensity will give you how intense the field is, how strongly the field is. Magnetic susceptibility, chi, will determine the interaction of any material with the magnetic field. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about magnetism and matter. We were actually comparing electric fields and magnetic fields and doing a comparative study. And we'll do that again in this class where we compare or we try to apply Gauss's law in magnetism. So what exactly is Gauss' law? Gauss' law, which we studied in electrostatics, states that the closed surface integral of E dot ds, that is the closed surface integral of E dot ds, is equal to q by epsilon naught, or simply the electric field will be equal to the net charge enclosed around a closed surface. Now the question is this applicable for the magnetic field also, or will it differ in the magnetic scenario? That is what we are going to do here. So we are going to apply the law, that is Gauss's law for electrostatics, similarly to magnetism here, and see if there is any other differences here. So we know that in electrostatics we can write this particular equation as q by epsilon naught only because of one reason. That particular reason is that since charges exist as single poles, that is, they exist as positive or negative poles alone, that is, monopoles for charged particles such as this do exist. But we do know that for a magnetic particle, there is no single such thing as monopoles, that is, no single monopoles exist. Till now, in principle, we can say that monopoles do exist. During the time of Big Bang, very close to that particular conditions, monopoles have said to be existed, and certain other conditions also, monopoles do exist, is the principle or theory we are propagating. But for now, we cannot actually find if there is any monopoles existing. So till that point, we are considering that there is no monopoles existing. Since there is no monopoles existing, we cannot write this particular equation just like this in the case of magnetism. That is, we can only write closed surface integral E dot ds is equal to q by epsilon naught only if we can draw any charged particle. Consider a Gaussian surface. Here I am considering point charge which is positive and a Gaussian surface which is spherical in nature. So we do know that all the field lines can emanate either out or into this particular source charge. If it is negative, then the field lines will be emanating inwards from infinity. And in this particular case, since it is a positive charge, field lines are emanating outwards. So this is the only reason why we can actually say that we can write E dot ds is equal to q by epsilon naught, because the net charge enclosed can emanate its field lines outwards to infinity. But that is, if we consider a Gaussian surface, there is a finite quantitative analysis for the flux lines or field lines coming out of that particular area. So we can say that it will be equal to, or it will be proportional to, the magnitude of the charge enclosed in that particular Gaussian circle. But in this particular case, that is for magnetism, if we apply that is integral B dot ds, then we cannot actually say this, because for a single charge in electrostatics, that is for a single pole that is positive or negative, the field lines can start from the source charge or end in the source charge from infinity or go to infinity. For a positive charge, the field lines can start from the source charge and end in infinity. Just like that, for a negative charge, it can start from infinity and end in the source charge. But if we consider a magnetic piece, that is a magnetic dipole, we know that no magnetic dipoles will ever exist as monopoles. That is, if there is a north pole, then immediately near it there will be a south pole, which means that all the field lines that is coming out of the north pole will be accounted for since it is entering through the south pole, which means that the field lines are all accounted for. Now, if we consider a Gaussian surface again around this particular material, let's say I'm considering a Gaussian surface like this around this particular magnet, then I have a clear account that the number of field lines leaving through here, that is, if two field lines are leaving from the north pole, then that much amount of field lines are returning back through the south pole, which means that the number of field lines exiting from that particular surface is again re-entering through another side, which means that all the field lines are accounted for. There is no field lines that is starting from one point and going out to infinity or going out to a particular point, because it is continuously forming a closed loop. It is coming back into the magnet and the number of field lines are accounted for. If +5 is leaving, then -5 is entering. So as much as it is leaving, it is entering, which means the net effect is 0. So that is why we say that we cannot clearly apply Gauss's law in magnetism like in the sense of electrostatics. We can also say that this particular theory, that is Gauss's law in magnetism, is a proof that monopoles do not exist because all the field lines are accounted for, not like in the case of electrostatics. So much more neater way to explain this is that we can clearly say, if we consider an area through which the field lines are passing like this, if we consider an area through which the field lines are passing like this, which means magnetic field direction is along that way, and then we can say that this is the ds element and this is the db element, then we can say that the closed surface integral, that is the closed surface integral of B dot ds will be equal to 0. This will be the proof for monopoles do not existing in nature because all the flux lines are being accounted for, which means if flux lines are entering into a Gaussian surface, it is exiting from that Gaussian surface, which means the number of field lines entering is equal to number of field lines exiting, or simply the summation of the field lines entering and exiting will be equal to 0. Hence, monopoles do not exist. Every field line is being accounted for. Simply, we can rewrite this equation in another way, that is in terms of summation. We can simply write it as summation of B del S will be equal to 0. But remember, if we are writing it for electrostatics, since monopoles do exist for electrostatics, we can say that E del S will be equal to Q by epsilon naught. Now this is the comparative study of electrostatic and magnetostatic fields in terms of Gauss's law, which you have to remember. The important thing, just a side note, is that if monopoles do exist and we manage to find them, then this particular equation will become in a different way. That is, this particular equation can be written as integral B dot ds will be equal to Qm mu. That is, this charge will be responsible for the magnetism that is being caused, or the magnetic field, or the magnetic aura that is emanating, and mu will be the permeability in a particular medium, which will act as the constant of proportionality here. So this equation only exists if monopoles exist. Since monopoles are not being found right now, we don't have this particular equation, and so we have to learn that B dot ds is equal to 0, and this is Gauss's law in magnetism, or simply we can say that this is the proof that monopoles do not exist. Now this was actually proven by Maxwell also in his future studies, who found out that del dot B is also equal to 0, or the divergence will be equal to 0, which if you have interest in physics, if you pursue physics even more further, you can study this in detail. So I'm not going to waste your time explaining about this. Anyways, this is also regarding Maxwell's equations, who contributed very much into the fields of magnetism and electrostatics, which is, he's the one who unified a grand unified theory for electromagnetism. So yeah, he was also a pioneer in proving that monopoles do not exist naturally anywhere around us. So simply integral B dot ds is equal to Qm mu, where Qm is the charge that is responsible for the magnetic field that is being produced, and mu is the constant of proportionality or simply relative permeability or simply permeability, magnetic permeability of a particular medium. If it is mu r, it is relative permeability. If it is mu naught, it is permittivity in free space. Anyways, now this proves that monopoles do not actually exist. Now we can also say that Maxwell also contributed to this particular cause. That is, he was the one who unified magnetism and electrostatics into the two sides of one coin. That is, he's the one who formed the grand unified theory of electromagnetism, which stated that del dot B is equal to 0. This is one more way of writing this particular equation. This is Gauss's law and this is Maxwell's equations. You don't have to learn about Maxwell's equation right now. If you're pursuing physics even further, you can learn about this equation and the contributions of Maxwell later down the road. So anyways, this is the operator called nubla, but we often pronounce it as del. It is not delta. Delta is this particular operator which looks like a triangle, but if the triangle is inverted, it is known as nubla, an operator which signifies divergence or curl and everything. So anyways, it's a mathematical operator. You don't have to remember all this. Just know that monopoles do not exist, and this equation does not exist if monopoles do exist. That is, the only thing you have to worry about is that monopoles do not exist as far as you're concerned, and the Gauss's law being applied in magnetism will give you the result integral B dot ds of surface integral of any quantity will be equal to 0. Now, since that was a very easy concept to understand, now we are moving on to magnetization. So what exactly is magnetization? Just like conductivity and certain other properties we learned for electrostatics, we are going to learn in magnetism how an object is magnetized, or what extent to an object can be magnetized. What are the properties that determine whether a material can be completely magnetized or partially magnetized, or however the material is being magnetized. Everything is studied here. That is, what extent a material can be made into or made similar to that of a magnet is known as magnetization. For example, I can clearly say that if I have a magnet like this, and if I take a small piece of iron nail and stick it onto the magnet, that is, it will automatically be attracted by the magnet. So if I stick that iron nail to a magnet, this particular iron nail now can act as a magnet and attract certain other paper clips or any other small magnetized objects or magnetic objects. So why is this happening? You can also see this phenomena with iron filings. That is, if I sprinkle a lot of iron filings around a magnet, it is actually the first group of iron filings sticking onto the magnet. But after that, the way the magnetic field lines are visible is by the iron filings sticking onto themselves. That is, they are sticking onto themselves like the iron filings are behaving like magnets. So how does this property happen? And why is this happening? To what extent can this happen? That is all determined by magnetization. How intensely or how much similar to a magnet can another object be made into. So for example, this is a permanent magnet, and since this iron nail is now acting as if like a magnet, how much is it magnetized? How much is it made into a magnet? That extensive nature of magnetization is what we are going to discuss here. That is, how and why that particular material behaves like a magnet and to what extent it can behave like a magnet. Everything is going to be discussed. So how can we clearly find out to what extent a material can be magnetized or made similar to a magnet? We can say that magnetization M is equal to vector M divided by V. Here, this particular vector M is the dipole magnetic moment or magnetic dipole moment. We can say that M is nothing but the dipole moment. M is the magnetic dipole moment of that particular material, and V is the volume. So V is the volume. Together, they will determine how much magnetized a particular object can be. For example, if we are again taking the case of an iron nail or iron piece, because it is highly magnetized, it can be highly magnetized. We can say that if you are taking the case of an iron nail, I can say that if I take a little piece, let's say I'm taking 1 cubic volume of 1 cubic centimeter cube of or 1 millimeter cube of this particular iron nail. That is, I'm taking a small piece which has unit volume in it, and I'm going to count the number of dipole moments inside that particular unit volume. Then I can say that inside that particular space, the number of dipole moments existing will determine how much a material can be magnetized. Or simply, I can say that if the number of magnetic dipole moments increase in a given space, in a given volume, then I can say that that particular material will be magnetized to a maximum extent. That is, that particular material can be magnetized heavily. If the number of dipole moments in that particular given volume is less, then I can say that that particular material cannot be magnetized to an extent. That is why iron can be magnetized to an extent and aluminium cannot be magnetized to a certain extent, or wood cannot be magnetized, because the existence of dipole moment actually determines if an object is magnetizable or not, if an object is magnetic or not. For that, also have to know what is exactly a magnetic dipole moment. So the simplest way to explain that is that imagine that I have a permanent magnet. If I break it in half, then still I will have two pieces, which is north and south. That is, I will have two smaller magnets, and if I keep on breaking them also, I will get each piece having north and south pole. That is, I will always have a smaller magnet which is significantly having lesser magnetic strength. But the point is that I still get smaller magnets, which means that this particular magnetic behavior or magnetic property is an intrinsic property. That is, this property is within the magnets themselves. So I can say that magnetic properties arise from within this particular material. I can say that every material is made up of atoms or molecules. I can simply go in even further, where these atoms and molecules are even developed of elementary charged particles such as electrons, protons and everything. Since protons are inside the nucleus and they don't move much, I am not accounting for them. Let's take the electronic contribution for now. So when electrons are being negatively charged particles and they are revolving around the nucleus, they are not actually revolving, but let's say for the time being, yeah, they are revolving around the nucleus. So we can say that due to their spin characteristic and their motion, that is orbital motion around that particular nucleus, it develops, that is, the electron actually develops a magnetic moment, which means that there are small tiny magnetic moments responsible within these particular magnetic materials. So these particular electrons are not alone. There is a group of atoms having a number of electrons, which means that all these tiny magnetic properties, that is tiny magnetic moments, add up together to form a net dipole moment. Dipole moment, or simply can be again assessed to be in a larger scale, we can just simply say that dipole moment can be said to be the torque experienced by a dipole to align itself to the field. The torque experience can be defined to be the dipole moment being experienced, but much more simpler or correct way of explaining that is dipole moment will give you clarity in terms of strength of the magnetic field. That is how strong the field is, how strongly it is attracting certain objects. So it will give you information about the strength of the field. And the second thing is that it will give you information about the orientation of that particular field. How, in what way, in what direction it is being oriented in. So basically dipole moment will give you an information regarding strength of the magnetic field and orientation of the magnetic field. And where is it arising from? It can be risen from, or it will be arising from, the innate intrinsic properties of an atom itself. That is, magnetic moment is possessed by an electrons itself. Because of their spin characteristic, it has a dipole moment. That is, it has magnetic properties which helps it behave like a magnet, a tiny magnet. and in net, that is in net effect, these tiny particles existing in groups will contribute to a net dipole moment. That is, in these particular magnets, inside them there are certain areas or certain regions which we group together called as domains. So these domains will have a net dipole moment in one direction. But for certain materials that have magnetic properties, these orientations of these different atomic groups or electrons cancel each other out since they are randomly oriented. That is why certain materials do not have magnetic properties existing in nature, but as soon as we apply an electric field or magnetic field towards that particular object, it develops a magnetic field innately. That is, it behaves like a magnet. So the reason for that is that the domains will align themselves to the magnetic fields. Domains and those reasons will be studied in depth in the coming classes. But for now, just remember, dipole moment will give you information regarding the strength and direction of the magnetic field. Since dipole moment is understood now, I can simply say that magnetization capital M will be equal to vector small m divided by V, where vector M is the magnetic dipole moment and V is the volume. So the number of dipole moments in a given volume will determine how much magnetized an object can be. If a material like iron can be taken into consideration here, the number of dipole moments for iron will be more in a given volume, which means it can be greatly or heavily magnetized. But if you're taking another example, like let's say copper or sodium, or let's say aluminum is also a metal. If you're taking any other materials such as that, then they have comparatively less number of dipole moments in a given volume. That is why they cannot be heavily magnetized. Maybe they can be slightly magnetized, but not heavily magnetized. So this particular property is because of, that is, the innate property of magnetism itself is because of the dipole moments existing. So that is what you have to remember before getting to magnetic intensity. That is, magnetization is equal to m bar divided by V. This will determine how much a material can be magnetized. If this is particularly clear, then we can move on to the next topic, that is magnetic intensity. How much intense a magnetic field can be made using a simple trick. So let's say I have a current carrying solenoid. If I have a current carrying solenoid, automatically it is understood it is going to behave like a bar magnet. So if I have a current carrying solenoid like this, it is understood that it is going to behave like a bar magnet. Now we already know that the magnetic field here will be, let's say it is B0. If I measure the magnetic field at the very center, I can see that the magnetic field in that particular solenoid can be written as mu naught Ni. That is, the amount of current and number of turns will determine the strength of that particular magnetic field. So simply, the number of turns in that solenoid and the current passing through that will determine the strength of that particular magnetic field for this particular solenoid. But my question is, what happens if I place a soft iron core or any iron material into that particular solenoid? I accidentally dropped it. Then what will happen to that particular magnetic field? Will it increase? Will it decrease? Will it stay the same? That is the question. So if I insert a soft iron core like this into the magnetic field, that is in the middle of that particular solenoid, what will happen to the magnetic field? Will it increase or decrease? So if you remember that point about magnetic dipoles, you can also remember that these particular iron materials have these intrinsic properties of magnetic dipole moment. Dipole moment is just waiting to be inside a magnetic field so they can experience a torque and they can align themselves to the magnetic field. I told you the particular magnetic material is made up of thousands of electrons, billions of electrons, each having a tiny magnetic moment, which means these atoms grouped together will have a net magnetic moment. But naturally existing, this particular dipole moment is randomly oriented in different directions. It is randomly oriented. But as soon as I introduce this into a magnetic field, remember this particular solenoid has a magnetic field. It has a magnetic field like this. So this has a magnetic field like this around it, which means if I keep a material inside that particular solenoid, it is going to experience that magnetic push or magnetic field. It is going to penetrate that material and the field lines will be passing through that particular material. And when the field lines are passing through that particular field material, then the magnetic dipoles, which are randomly oriented in different directions, that is magnetic dipole in different directions, kept in a magnetic field, will experience a torque. They will align themselves in the direction of the field, which means that these particular randomly oriented dipole moments, that is the group of randomly oriented dipole moments, will now align themselves in the direction of the field, which means they will have a common direction. All these will be pointing in that particular direction. Remember, this area is when particular soft iron core material or any iron material here, because it will have a lot of magnetic dipole moments. That is why I took that particular material. So anyways, that particular iron material, when kept outside the magnetic field, it is randomly oriented. The dipole moments are here, there, there. It is randomly oriented, which means that the net effect is cancelled out. Since one is acting this way and one is acting this way, they cancel each other out. But when introduced into a magnetic field, the dipole moments are aligned, which means the dipoles are experiencing a torque and they are pointing towards a common direction. That is the direction of the field, which means they will also develop magnetic properties. That is, this particular dipole moments being aligned in the direction of the field will have a small magnetization effect, which will produce a small magnetic field also, which means the net magnetic field experienced here will be the sum of the magnetic field of the solenoid plus the magnetic field of the material, which is now just magnetized, which is made into a magnet. So it will be the sum of magnetized material, magnetized soft iron core plus the magnetic field of the solenoid. So now if I ask for the magnetic field B in that particular region, it is not just B naught, but it is B naught plus Bm, where Bm is the magnetized field of this particular soft iron core. Now, before getting into any further things, we have to know one more quantity, that is magnetic intensity. So, what is exactly magnetic intensity? Just like the word suggests, magnetic intensity will give you how intense the field is, how strongly the field is. Basically, here the magnetic intensity is more compared to a region really far away. Magnetic intensity will give you details or information about how intense, how strong that particular field is. In this particular case of the solenoid, we can say that the number of turns and the current passing through that will determine the strength of that magnetic field of that particular solenoid. So magnetic intensity here is determined by the number of turns and the current passing through that. Just know that magnetic intensity is how intense the field is. And now we can represent that magnetic intensity, that is magnetic intensity is represented by the letter capital H. Capital H will determine how strong the magnetic field is for that particular material or around that particular material. So here I'm going to write this equation in terms of magnetic intensity, how strong that particular magnet is. So I can write that instead of mu naught Ni, I'm going to write it as mu naught H. That is how strong that particular field is. So I'm going to write B naught as mu naught H in terms of magnetic intensity. And I'm going to write Bm in terms of something. Simply I can say that Bm will be directly proportional to magnetization M. Or simply by introducing the constant of proportionality, I can say that it will be equal to mu naught M. So we have an equation. Now I can write or explain this in detail and write it as mu naught H plus mu naught M. Or simply I can write it down as it is equal to mu naught is common, I'll take it outside, H plus M. But again, I told you I want an equation in terms of magnetic intensity, how intense that particular field is. So what do I do for that? So we have to find a relation between this magnetization and magnetic intensity. Luckily for us, we already know a relation, that is, so M is actually directly proportional to magnetic intensity, and we can say that M is directly proportional to H. Because how strong the field is will determine how heavily material can be magnetized. That is, if I keep an iron nail near this particular solenoid, if this is a weak solenoid with less number of turns and less current passing through that, that iron piece or iron nail will not be heavily magnetized. But if it is more number of turns and more current passing through that particular solenoid, then I can say that if I keep this iron nail near to that particular solenoid, it will experience an intense magnetic effect and it will be magnetized intensively, or it will be heavily magnetized. So I can say that magnetization is directly proportional to magnetic intensity, or simply by introducing a constant of proportionality, I can say that M is equal to chi H. That is, this particular quantity is known as chi, or here the particular symbol chi is known as magnetic susceptibility. So it is known as magnetic susceptibility. That is, how easily or how effortlessly the field lines can penetrate through a material, how much material is susceptible to becoming a magnet, how much this particular material is susceptible to cooperating with the magnetic field is determined by the chi value. So we can say that the chi value will determine how easily the magnetic field can interact with that particular material. If it is heavily interacting, it will be positive. It will be poorly interacting, then it will be negative. So if it is 0, then it is a weaker interaction. So basically all you have to know is that magnetic susceptibility chi will determine the interaction of any material with the magnetic field. So that is what chi actually means. And now we already have an equation relating M and H. From this you can also find out the value of chi. Chi is equal to M by H. That is one more relation. If we have one relation, we can find out the other relation. So I'm not going in depth about all those. The relation we are focusing on right now is that M is equal to chi into H. From that we can find the value of chi for any material depending on the magnetization and magnetic intensity. But now, let's come back to the derivation. And now we have to find a relation between M and H, which we just did. That is, M is equal to chi H, which we will substitute here. Then we can write mu naught into H plus chi H. Or simply we can rewrite it as mu naught H into 1 plus chi. Now this is the equation regarding the magnetic intensity of any material written down. So the net magnetic field at any particular point, if there is any material like a soft iron core inserted into a solenoid, just like this, if the magnetic field is enhanced using any other material, we can use this particular equation to find that out. Susceptibility, that is how easily susceptible that particular material is to the magnetic field. The magnetic intensity of that particular material will determine, that is all together they will determine the net magnetic field or magnetic field strength of that particular area. So the only thing you have to remember from these classes are that there is something known as magnetic dipole moment, how it exists, and groups of these particular atoms working together can form domains. So magnetic dipole moments, that is they collectively dealing in groups, is known as domains, and these particular domains being aligned with the magnetic field will determine the magnetization effect, that is how closer that particular material is to becoming a magnet. So these are the few things you have to remember about magnetic materials, magnetic behavior, and how closely an object is becoming a magnet. So I hope you have understood everything I have just taught you here today, and I'll see you all in the next class with more topics regarding magnetism. So till then, I'll see you all in the next class with more topics. Till then, bye.